This is going to be a kind of a quiet review of just the very basics of algebra that go into stormwater calculations. And so, having done Hydrograph, you realize how much of this is done for you, and you have to realize how important using standard units is. So I will not force upon you how you're going to get things into square feet or square meters, but I will let you know that the necessity of doing it out of habit, and if you need a party trick to do it, use the party trick, is important, because I got that mismarked there. So you want to get things in square feet, square meters, or cubic feet, cubic meters, or cubic feet per second, cubic meters per second, etc. And you generally do that by getting things, this comes from getting things into square feet and then feet per second, when of course the square feet over 1 times feet per second equals cubic feet per second. Or to getting them in square meters over 1 times meters per second equals meters cubed per second. So that single thing that comes out essentially out of estimating of all the kind of basics that we have in civil, getting things into base units for your most defensible calculations, and then getting them back out to base units like acre feet or square yard inches is an important thing. So let's look at some of the typical problems that will be on an exam, and one would be the fact of you have a velocity and an area in one reach of pipe and a velocity and an area in another reach of pipe, and it is a system where all the flow here ends up at all the flow there. So this is A1 and this is A2. You can know that the velocities will be inversely proportional to the ratio of the areas, or you know that if you have twice the area, you have half the velocity, or half the area you have full, or half the area of twice the velocity. You have to remember that's based on area, however, not based on diameter. So for a circle, this could also be written to V1 times diameter, right, over 2 squared times pi, couldn't it? So if you go over here, that would be the same thing, V2 times diameter over 2 squared times pi. And so it is not only, the velocities are not just based on the ratio of the areas, they are based on the square of the ratios of the diameters or the radiuses. Now that generally comes up more often than you would think, as in flow problems. Very often you will have a very large pipe coming down to a very small pipe, coming down to an even smaller pipe. And so you can realize that the velocities are related to each other by the square of the diameters. So if you know this is V3 and this is V1, V3 to V1 is going to be, V3 is going to be more, so it's going to be the diameter on the large diameter is going to be here, V1 to D3, and then this will be squared. So that ratio is going to be true. Let's check that. 1 is greater than 3, and we know that V3 is greater than 1, so this is going to be true, which is the same as, if we think about it, V3 to V1 equals area 1 to area 3, because V3 times A3 equals V1 times A1. So that's one basic calculation that one can very quickly come to by understanding this relationship here is oftentimes seen this way. Alright, so basic flow problems. Given Q and A, determine V. Given V and A, determine Q. And then also given a system, determine that. So that's one type of problem. Back to home here. Edit. All right, so one type of problem. Q equals V times A. That's called the flow continuity. It has one separate thing that you need to realize, that very often you could have Q1 and Q2 coming together into Q3. And so you have to know that Q1 plus Q2 equals Q3. And of course Q1 equals velocity 1 times area 1 plus velocity 2 times area 2 equals velocity 3 times area 3. So this is typically done by a link and node that you saw in Hydrograph. And you can do other problems that are diversions that split. You have Q1 in and it goes out to Q2 and Q3. That's what you saw in most of your ponds. You had some sort of flow rate in, some sort of storage, but when it was full, pretty much you had some water going out the pipe and some water going out the weir. Alright, I guess we'll call this Q in, Q out 1, Q out 2. Alright, so flow continuity problems. Alright, so besides flow continuity problems, we also had this concept of, and we've covered it a little bit, you've done it in Hydrograph. We know that the Q peak is equal to the rational coefficient times the intensity times the area in acres. And that gets you CFS, and we've done a lot of rules of tens. So we said that if it was all pavement and it was a 100-year storm, you got 10 CFS of an acre. We know that the total runoff of a 100-year storm turns out to be about a half acre foot per acre pavement. So we did that. We should know our design storms by now around here. A 100-year storm is 6 inches in a 24-hour period. And we know that the 25-year storm is 4.8 inches in a 24-hour period. And the 10-year storm was around 2.8 in a 24-hour period. So we know that we use these kind of analogies to go down from our 1/2 acre foot or down from our 10 CFS. So we should know how to do weighted averages based on curve numbers that we said for pavement were 98 and meadow over 58, thereabouts. They go down lower from that. All right. We talked then about Bernoulli's equation. Okay, and Bernoulli's equation, by rote, at the very least, by rote, we know that the elevation energy per pound of material plus the pressure energy per pound of material plus the velocity energy per pound of material plus any head in the pump is going to equal, at a second point, the the elevation energy per pound of material plus the pressure energy per pound of material plus the velocity energy per pound of material plus any head loss that has occurred through there. And we have to know that head loss is equal to some constant times the velocity head at any one point. We need to know that by rote. We need to know how to do very simple calculations with the reservoir, where in fact you know off some datum here, you know an elevation there, Z1, you know an elevation there, Z2, and you know the change in height equals Z2 minus Z1, which, if there is no friction, leads to that fact of velocity equals the square root of 2gh. But we know that in reality, based on some energy loss through the pipe, the velocity is going to be equal to some constant times the square root of 2gh. But we have to remember that flow equals velocity times area. So once we calculate the velocity, we need to know the area of the pipe, and everything must be in square feet or square meters, or this does not work. We should know very quickly how to convert CFS to acre feet. We should know very quickly how to convert CFS to gallons per minute. And we should know pretty quickly how to convert CFS to million gallons per day, MGD. We know that these are all standard, right? And so we need to be able to very quickly and efficiently look at numbers that make sense using conversions in our calculator and some logical sense. Another formula that we've looked at is in fact the power formula, that in English, if you're given CFS and H head in feet of head and gamma in pounds per cubic foot, we know that Q gamma H over 550 gets us horsepower, and we know that 1 horsepower equals 746 watts. This is the power equation. And in fact, we know that for a pump with a free water surface someplace down here, a pipe that looks like this, a pump that looks like this, we know that the water always has to flow down pressure. So the energy grade line is going to be one velocity head above the exit. It's going to go up, it's going to come down at the pump, and it's always got to flow down. It actually would start there and come down. So the energy grade line always flows down except when it goes through the pump. And we know that the slope of the energy grade line, the slope, is proportional to v squared over 2g. So as the velocity goes up, you pump more and more water, you have a slopier energy grade line. So we'll finish this up in a second here. We're going to go to home, new slide again, go to here. So those are the basic equations that we've talked about. We know that a hydrograph is a graph of flow versus time. Therefore, the area underneath, if you have cubic feet per second times seconds over 1, the area underneath is cubic feet. So we know something about the integration of the hydrograph. And like a lot of these things, we're learning these concepts so we can apply them again and again, specifically next semester when we look at the integration of a load curve in pounds per foot being pounds. So this is a hydrograph, and we know that in reality when we use the storage equation, which is flow out or flow in minus flow in times the change in time equals the change in storage. We know that happens is our inflow hydrograph looks something like this, and our outflow hydrograph looks something like this, and we know that the areas under the inflow and the outflow hydrograph are equal if there is no kind of storage per se, no permanent storage. So we know the area of the under the hydrograph, and that's what you saw in hydrograph when it basically told you required storage to hit certain different types of peaks. All right, so those are the equations. There is an equation sheet provided to you. Learning to do things like this, always bracket your equations. And I know you love to do this, bracket equations. In other words, know a couple of things. If you throw a ball up at 68 miles per hour, which is the same as 100 feet per second, it will go up 155 feet because 100 squared divided by 2 times 32.2, they tell me, is equal to 155 feet. Know that's true. Also know the square root of 2gh, or in fact know that for a metric, a drop of 0.5 about meters leads to pi meters per second, and for feet, 0.15 feet leads to pi feet per second, and this is a square root relationship. So with that, I will finish out the last couple of minutes to talk about, and we'll have a chance next semester when we talk about water on roofs, to talk about why is it in fact, having gone out and looked at Professor Lewin's discussion of waterfalls, why is it in fact waterfalls are so damn cool? Well, all kinds of different reasons, I'm sure, but partly it's because of this. If you have water with a certain area coming down, area 1 there, and a velocity, let's say equal to v1, we know that area 1 times v1 is some value q, and as this goes down, drops a certain height h, we know that the area at 2 times the velocity at 2 has got to be equal to the area at 1 times velocity at 1, and so our area at 2 must be less, and so we get what's called a nape. And what happens eventually is the water cannot hold together, and it tends to break up into droplets, and so you get some of that aeration, etc., that you have in a waterfall. So Bernoulli's equation, amongst all other things, explains a little bit about waterfalls. And my assumption is that with Snell's law, which we looked at earlier in the semester, and some of you didn't hang with that, I would suggest you go back and look at it again. Snell's law and Bernoulli's equation I think you figure out why people walk 5 miles up into the mosquito-infested jungle to look at a waterfall. Thanks for listening.